Today we will discuss about the quantum numbers. The word quantum is derived from the word called quantum, which means energy packets. So here the some set of numbers are there. We are going to discuss that quantum numbers. These are the terms which helps us to define the size, shape, orientation and energy of the shell. So there are four types of, basically we can say there are four types of quantum number. That is principal quantum number, azimuthal quantum number, magnetic quantum number, and another one is spin quantum number. Here principal quantum number, that is denoted as n, it helps us to determine the size of the cell. It helps us to determine the size of the cell and energy also. Radius of the cell can be derived as the formula m square h square upon 4 pi square m e square z. For hydrogen atom, if we put the formula, we will find that radius is 0.529 Armstrong. Similarly, we can determine the energy of the cell also. We can determine the energy also. Energy of cell too. That energy formula for nth cell will be minus 2 pi square m e to the power 4 z square upon n square h square. For hydrogen atom, E or energy can be determined as minus 1312 by n square. That is the value. Now we will discuss about what is principal quantum number. As I told you, the principal quantum number helps us to determine the size and energy of the shell. So we can say that the n, which is principal quantum number, is also helps us to define the period number or the number of cells present. So we can determine the period number or number of cells present. For that example, we can say, we know that there is two cells, K cell, L cell, M cell, N cell. For that, principal quantum number will be defined as 1, 2, 3, 4. Always remember that the value of n cannot be 0 or fraction or decimal or negative. So the value of n cannot be 0, fraction, decimal or negative. And discuss about azimuthal quantum number. It is denoted as small l. It is also known as subsidiary quantum number or angular quantum number. It is normally the value of azimuthal quantum number, that the range of azimuthal quantum number varies from 0 to n minus 1. So we can say the value of L should be less than the value of n or principal quantum number. So we can say that for K cell, the value of principal quantum number is 1, and for that azimuthal quantum number will be considered as 0. Now for L cell, principal quantum number is considered as 2, while the value of L will be considered as 0 and 1. Similarly, for M cell, the principal quantum number will be 3 and our azimuthal quantum number is considered as 0, 1, 2. For N cell, principal quantum number is 4. Our azimuthal quantum number will be considered as 0, 1, 2 and 3. So indirectly we can say that azimuthal quantum number nothing else, it determines the number of subcells present in a cell. How many subcells are there in a cell? That is determined by the azimuthal quantum number. We can see that the K cell has one cell, means principal quantum number, which have one subcell, and that is we are naming that 1s. Similarly, we can say that for 0, if L is 0, that is determined as S. For 2, 0 is considered as 2s subcell and 1 is considered as 2p. So we can say L is 1 for p subcell. Now for 3, we got 3 subcells, that 3 azimuthal values, that is 0, 1, 2. So we will get that 3s, 3p and 3d. That L is 2 for D subcell. And for 4, we get 4 subcells, that is 4s, 4p, 4d and 4f. That we can say that L equals to 4 for F subcell. Simply, we can say that azimuthal quantum number is nothing just to determine the number of subcells that is present in a cell. As from the atomic structure, we found that the electrons are revolving around the nucleus in an atom. As the number of electrons increases, there is a possibility they will repel each other. To avoid that, Neil Bohr decided that he said that what electrons are revolving in a particular path, that he said orbit. In the orbit they are revolving, and then further we divide that shell into subcells. N is the cell that is further divided into subcells, that we are naming SPDF. What for S subcell, the azimuthal quantum number, which is the second quantum number, is 0. For P subcell, L is 1, D subcell, L is 2, F subcell, L is 4. That is all about the azimuthal quantum number. Now, what is the use of principal quantum number and azimuthal quantum number? Now we will find what is the importance of azimuthal quantum number and principal quantum number. Now consider, when we are writing any element electronic configuration, consider I am writing oxygen or writing helium. So helium is 2 electrons. Previously we write that 2. It means it is the first cell which contains 2 electrons. That's why we will write 1s 2. 1 denotes that the cell number, S denotes the subcell or azimuthal quantum number, and this is the number of electrons present in that cell or subcell. Now consider I am writing oxygen, that is 8. If I am writing 2, 6. Previously will write like this. Now for first cell we have one subcell, 1s. For second cell we have 2 subcells, that is 2s and 2p. From the above example, we found that S has the capacity of maximum 2 electrons. So we will write that S is 2. Similarly, this S should have capacity of 2. 6 minus 2 is remaining 4. So in this way, we can write out the configuration. We have to remember that the capacity of accommodating electron for S subcell is 2, for P it will be 6, for D it will be 10, and for F it will be 14. So how many electrons can accommodate one subcell? Always remember, S subcell can accommodate maximum 2 electrons. It can be 0. P can accommodate maximum 6 electrons. D can accommodate maximum 10. F can maximum 14. Now, what is the full form of S? That is sharp. P for principal. D for diffused. Fundamental. That is the full form of these subcells. Now we will discuss how to write the configuration in increasing order of energy. Always remember that we are finding the numbers, but when we have to arrange them on the basis of increasing order of energy, because energy is inversely proportional to stability. As the energy increases, stability decreases. So we have to find out that this should be arranged in increasing order of energies. Now, we know that first cell contains one subcell, second cell contains two subcells, that is 2s and 2p. Third cell contains 3s, 3p and 3d, three subcells. Fourth cell contains four subcells, that is 4d and 4f. Similarly, fifth cell will contain 5 subcells. Sixth cell will contain 6 subcells. Seventh cell will contain 7s, 7p, 7d, 7f, 7g, 7h, I. Now 8s. Each shell represents each period. In our periodic table there are 7 periods, so we will use up to the 7s. Now we will arrange them in increasing order of energies. We will follow the arrows to get the energy series. Now we will start with 1s, it is the least energy, then 2s, then comes 2p, then 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s. Four F, 5d, 6p, 7s, then comes 5f, 60, 7p. By following this method, we wrote all the increasing order of atomic orbitals. Now, what is orbital? Previously I told you about the orbits. Electrons revolves around the nucleus in a particular path. That path is called orbit. But orbitals are the region where the probability of getting electron is higher, that is more than 90%. If the region or the area where we can find out the electron, that is called orbitals. Similarly, some regions are there where we cannot find the electron. Those regions are called nodes or nodal surfaces. Now this is the increasing order. Now there is another question: how do you define that this sequence is correct or not? Let us find out a series that 3s to 3d. Now we will calculate the order. When I am writing a 3s, you will find this indicates the principal quantum number and this indicates the azimuthal quantum number. So we will find that the total energy is the sum of principal quantum number and azimuthal quantum number. Let us find out the energy levels of these four orbitals. 3s, 3p, 4s, 3t. Now, n plus L value. N is 3 here. L will be 0, that is yours 3. 3 plus 1, that is 4. 4 plus 0 is 4. 3 plus 2, 5. When I am writing in increase, if we are writing this in ascending order, the 3 will come, then 4, then 5. Now, when two of orbitals have same energy value, then we will say lesser the n value or lesser the principal quantum number, lesser is the energy. So when we will find the n plus value will remain same, then we will find whose n value means principal quantum number is less. The lower is the principal quantum number, lower will be the energy. In this case, we will find 3 has 3s subcell lesser than 3p and 4s have equal energy. In that case, this have lower n value, that is 3p is lower energy, 3p has lower energy than 4s than 3d. So this is the mathematical sequence that we did previously. Now we will discuss about magnetic quantum number. That is denoted as m. It represents the number of orbitals present in a subcell. It is represented by the symbol m, and the range of magnetic quantum number is minus L to plus L. So we can say that the total number of orbitals equals to 2L plus 1. Now we will determine how it is calculated. Now see, if I am writing K cell, the n value will be 1, L value will be 0 because it varies from 0 to n minus 1. Now m value will be minus L to plus L, so it will be 0. Now for L value, n is 2, that's why the value of L becomes 0 and 1. The magnetic quantum number for L is 0. For this it will be minus 1, 0, plus 1. Now if you will discuss about M cell has the principal quantum number 3. Then the L value, azimuthal quantum number value will be 0, 1, 2. So our value becomes 0, minus 1, 0, plus 1. -2, -1, 0, +1, +2. What we are finding that K cell has one azimuthal quantum number and has one magnetic quantum number, that we are saying orbital. But when we are discussing about L cell, it has two subcells, so two cells and two subcells, and these have these orbitals. So we know that the value of L is 0 for S subcell. Now for S subcell, it has one orbital. We can find out 1s, 2s and 3s has one orbital. So we can say when the for the S subcell, L or azimuthal quantum number is 0 and it has one number of orbitals. Now when we are saying that L is 1, we are saying that it is a p orbital. For p orbital, we are finding 3 magnetic quantum number. It means it has 3 number of orbitals. Also we are finding in 2p and a 3p. So we can say in these two cases we are finding that p has 3 orbitals. Now in case of D, we can find it. There is 5 orbitals. 1, 2, 3, 4, 5. So basically magnetic quantum number is nothing to determine the number of orbitals present in a subcell. What are the names? For S, it is spherical set. So it has no, spherical means it is identical. For P, we got that 3 orbitals. That's why these are named as on the basis of axis px, py, pz. Similarly, in D subcell, we found 5 orbitals. Those are named dxy, dyz, dzx, dx square minus y square and dz square. For F subcell, we found 7 number of orbitals. That's why these are named fxq, fyq, fzq, f x whole into y square minus z square, f y whole into z square minus x square, f z whole into x square minus y square, and last one is fxyz. So these are the names of orbitals obtained by these subcells. For S, it is a spherical shape. For P, it is a dumbbell shape. These are dumbbell cells. It is in double dumbbell shape. It is triple dumbbell shape. Now we will find out the spin quantum number, that is denoted as spin or F. It is normally nothing the orientation or the direction of revolving of electron around the nucleus. Electron may revolve around the nucleus in clockwise or anti-clockwise. That's why it is considered as plus half for clockwise rotation, minus half for anti-clockwise rotation. This is all about the spin quantum numbers. Now we will discuss about shape, orientation and nodes. I told you that orbitals are the region where the probability of getting electron is higher or more than 90%. Similarly, the region where we don't get electron is called node or nodal surface. So to find the number of nodes, our formula is L minus 1. So we can say we have for determining the S subcell, if we are finding this S subcell, first 1s orbital. For 1s, number of nodes will be, I am writing the number of nodes, that for 1s, number of nodes, n value is 1 minus s value is 0 minus 1 equals to 0. And we know that S is spherical and it has no nodes, means throughout the 1s orbital all the electrons are uniformly spread, so it is non-directional. Always remember, S subcell is non-directional. Now 2s, let us find 2 minus 0 minus 1, that is 1. For 3s we are getting 3 minus 0 minus 1 is 2. So as the S subcell, the 1s, 2s, 3s, we are going to from 1s to 3s, the number of nodes increasing. So it means the for uniformity through the S subcell is decreasing. That's why the number of nodes increasing. Now we will find out the P subcell. For P subcell, we know that P is dumbbell set, and we can clearly see this is the nodal part and these two parts are called lobes. These two parts are called lobes. So we can determine that 2p, 3p and 4p, the L value will be 2 here, minus L value is 1, minus 1 equals to 0. For 2p there is no node. For 3p, minus 1 it becomes 1. 4 minus 1 is 2. So we can see again, as we are going from 2p to 4p, the number of nodes increases, it means uniformity decreases. This is the shape of a 2p or P subcell. Similarly, we can determine the number of nodes for d orbitals and f orbitals.